We think of cold as just, well, the absence of heat. But what if there's a temperature so low? It's actually a fundamental speed limit for the entire universe, a point where the laws of nature themselves tell you, sorry, you can't go any further. That's absolute zero. And it's not just some number. It's a journey to the very bottom of reality.
So what is this ultimate cold? Officially, it's 0 on the Kelvin scale. Now, the Kelvin scale is what scientists call the absolute thermodynamic temperature scale, which is a fancy way of saying it starts at the lowest possible point. There are no negative numbers. 0 is it. It's the floor. And to put that into terms you might be more familiar with, that's minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. I mean, that is a cold so deep, it's colder than the most empty, desolate voids in deep space. It's almost impossible to even wrap your head around. And here's what's so crucial to understand. This isn't just some arbitrary number on a thermometer that we humans came up with. Absolute zero is a real, physical boundary. It's a hard stop that's literally woven into the fabric of the universe itself. Okay, so to really grasp this ultimate limit, we have to back up a little and ask a more basic question. What even is temperature? Turns out it's not just about how hot or cold something feels. It's about a frantic, invisible dance that's happening all around us all the time. At its core, temperature is motion. Seriously, everything is made of atoms and particles, and they are constantly jiggling, vibrating, and zipping around. Temperature is just our way of measuring the average energy of that chaotic movement. The more energy, the faster the jiggle, and the hotter it feels. Think about a cup of hot tea. The water molecules in there are going absolutely nuts, bouncing off each other like they're in a mosh pit. Now picture a block of ice. Those exact same water molecules are still moving, but now they're locked into a crystal grid, just kind of vibrating gently in place. So when we cool something down, all we're really doing is convincing those atoms to chill out. So what happens when we keep pushing this? When we keep sucking more and more energy out, forcing that atomic motion to get slower and slower and slower? Well, as you can probably guess, this is where reality starts to get very, very weird. At room temperature, everything behaves like you'd expect. At 0 Celsius, water freezes into a solid. You get down to minus 200 and most things are incredibly brittle solids. But as you get really close to the bottom, down past minus 270 degrees, the familiar classical rules of physics start to fall apart, and the strange, almost magical rules of quantum mechanics begin to take over. Now, you might be thinking, okay, just keep removing energy, and eventually everything will stop moving completely, right? Perfect stillness? But here's the thing. This is where we slam into a massive, fundamental roadblock, a law of the universe that says, nope, not gonna happen. And this really is the million-dollar question. If absolute zero is the point of minimum possible energy, why can't that minimum be an actual, honest-to-goodness stop? Why does there always have to be some little bit of motion left over? The answer? Well, it takes us right to one of the weirdest cornerstones of physics. You've probably heard of this one, Heisenberg's uncertainty principle. It's not about our equipment being bad. It's a fundamental rule of reality. It says there's a cosmic trade-off. The more you know about where a particle is, the less you can know about where it's going, and vice versa. You can't have both with perfect precision. Okay, so let's follow the logic here. Let's say, just for a second, that we actually managed to bring a particle to a perfect dead stop. If we did that, we would know its momentum with absolute 100% certainty. Its momentum would be exactly 0. Now, if you know its momentum is exactly 0, the uncertainty principle says its position should be completely unknown. But wait a second. For something to be stopped, you have to know where it is, right? So in this imaginary scenario, we would know its exact momentum, 0, and its exact position at the same time. And there it is, the paradox. The universe simply forbids that level of certainty. You cannot know both things perfectly. So what's the conclusion? The premise must be wrong. Particles can never, ever truly stop. Perfect stillness is impossible because nature itself won't allow it. This tiny, unavoidable, permanent jiggle that every particle has, even at absolute 0, has an incredible name, zero-point energy. And it's not heat in the way we usually think of it. It's a fundamental quantum tremor, an energy that's part of the very fabric of space-time that you can never, ever get rid of. So if perfect stillness is off the table,
what does happen when we get ridiculously close to absolute zero. This, my friends, is where the universe decides to put on a real show. Matter starts to shed its everyday properties and transforms into new states that are just bizarre. What if the wildest things we see is a fifth state of matter, something predicted by Bose and Einstein decades before it was created? It's called a Bose-Einstein Condensate. You cool down a cloud of atoms so much that they kind of lose their identities. Their quantum waves overlap and they all start acting in unison as a single giant superatom. And when they're in this state, the quantum world, which is usually hidden away at tiny scales, becomes big enough for us to see. All these particles move in perfect lockstep, like a beautifully choreographed ballet. They can even do things that sound impossible, like passing right through a solid barrier. It's matter behaving like one giant cohesive wave. But wait, there's more. Down near absolute zero, some materials become superconductors. Electricity can flow through them with absolutely zero resistance. A current started in a loop would literally flow forever. Magnets will just float above them, suspended in midair. And some liquids, like helium, become superfluids, flowing with zero friction at all. They can even crawl up the walls of their container and spill out the top. It's like physics turns into straight-up magic. Now, seeing all this incredible stuff, you can imagine the temptation to just get there, to finally hit exactly 0 Kelvin. But here's the final twist. Despite getting so close, we can never actually arrive. It's like a finish line that moves away from you the faster you run towards it. And there are a few hard reasons for this. First, the colder something gets, the harder it is to remove the next tiny bit of heat. It would literally take an infinite amount of energy to remove that very last bit. Second, our best cooling methods still accidentally add tiny bits of heat back in. Third, you've got that pesky 0-point energy that can never be removed. And finally, the universe itself isn't at zero. It has a background warmth of about 2.7 Kelvin, a faint afterglow from the Big Bang. You just can't get colder than your surroundings. I mean, we've gotten mind-bogglingly close, down to about 1/10 billionth of a single degree above absolute zero. That's close enough to see all the quantum weirdness happen. But that final impossible step to exactly zero, it's always just out of reach. So, what's the big takeaway from all this? Chasing absolute zero isn't really about hitting a specific number. It's about exploring that blurry line where our everyday world dissolves and the quantum realm begins. It teaches us why perfect rest is impossible, and it reveals how totally new kinds of reality, superatoms, frictionless liquids, can emerge from the cold. It's the bedrock of quantum reality. In the end, absolute zero isn't a destination we can ever reach. It's more like a concept, a fundamental truth that shows us the universe is always buzzing, always alive with this deep, unremovable quantum energy. And it leaves you with this incredible question. If perfect stillness is impossible, what other impossible things are hiding down there in the quantum realm, just waiting for us to find them?